Okay, good morning. Let's get started. So first of all, maybe you have seen the release of homework 4. So again, please start as soon as possible. And also, you need to think about the final project report, right? And again, so don't worry that, okay, if your Kaggle computation rank is too low, or if your exploratory project doesn't seem working, right? That doesn't matter. We just want you to go through some kind of like a practicing procedure, right? So we do want to say a few sections in your final project report, right? As listed in our course webpage or syllabus. Please double check with that. So someone are concerned about grading. Actually, the grading principle is very simple. We just look at if your final report contains those sections, right? If it doesn't contain those sections, you'll get deducted. Right? If it contains, you get all the points. And of course, for the Kaggle computation, a high rank will give you some bonus. Okay. So today we're going to talk about starting today we're going to spend a few lectures talk about artificial neural networks. Right? So perhaps it is the dominant machine learning technology right now. Right? Although it wasn't dominant technology maybe 10 years ago. Right? It's interesting that the neural networks were invented a long time ago. Right, and in 1980s, it is very prosperous, right? And many researchers in artificial intelligence they're studying on neural networks. And then in 1990s, with the invention of support vector machines, the neural networks, and people forget about neural networks for about 20 years, right? And until maybe 10 years ago, Geoffrey Hinton and his team showed that using deep neural networks can dramatically improve the performance of some tasks like image classification. Then the neural network has researched, and then there are a lot of like resources, attentions are putting on neural networks, and right now they become like some kind of dominant technique. Right? So when people talk about artificial intelligence, actually they're talking about machine learning. When people talk about machine learning, they most likely are talking about neural networks, but we shouldn't will them in that way, right? Machine learning contains a lot of topics, right? Neural networks is just one branch, and one kind of like a booming branch right now, but I suspect it won't last for long. There are a lot of like bottlenecks coming on in the neural networks as well. So perhaps after not a very long time, there will be another type of machine learning models come out and become dominant again. Right? So this is kind of like many methods are competing each other. In some period of time, people will this kind of like pillar for a bunch of problems, and then later on people find this is bad, they cannot address this problem, we find bottleneck and then switch to another things. It's kind of alternating trends. Okay, so before we talk about neural networks, let us just look at what we have discussed so far. Right, we have discussed quite a few learning algorithms so far, right? We don't want to mess around, right? We want what we have learned to be well organized, right? So first, from the algorithm perspective, right? Here are a bunch of learning algorithms we have discussed, right? Decision trees, AdaBoost, bagging, those are ensemble learning, least mean square, this is about linear regression. Perceptron support vector machines are about linear classifiers, right? And kernel SVM and kernel perceptron are smart methods that generalize linear classifiers to nonlinear classifiers. Right? Throughout this discussion about the learning algorithms, we also I'm seeing several important concepts in learning and principles, like what is the concept of overfitting, right? What is mistake bound learning, right? What is the concept in computational learning theory, like PAC learning, right? Sample complexity, and the choice of a hypothesis space was the definition of VC dimension, right? So, and then we talk about what we are concerned in machine learning. It is about generalization error, right? So the training error, we shouldn't just optimize training error, right? We should look at the generalization error, right? That motivates us to develop the support vector machines, right? And then to be a more generalizable framework, we use the so-called regularized empirical risk minimization principle, right? So among those algorithms, right, we know that most recently we'll talk about how do we learn linear models, like linear regression or linear classifiers. And of course, linear models are quite restricted. Right? In practice, you can really assume that the output of interest you want to predict only has a linear relationship with the input features, right? So of course, we want our model to be capable to capture those nonlinear relationships. So one way of doing that is to apply the so-called kernel trick, right? As we emphasized again, we try to come out some kind of feature mapping, right? Transform the original input features into some higher dimensional space. If that transformation is smart enough, we believe that in the mapped feature space, we can find a linear classifier which will separate positive and negative examples, right? So the general trick of doing so is called kernel method, right? But there could be another way, right? There could be another strategy. Right? Why not we should stand on linear models? Right? Why not we just construct a nonlinear model from scratch? Right? So first I want to ask, are decision trees linear models? Are decision trees linear classifiers or linear models? Why? Yes, exactly right. So remember, we have showcased a boundary classification boundary for decision tree, right? Although decision tree is constructed in a very intuitive way, but the classification boundary can be quite complicated. It could be a box, right? It could be some weird polygon, something like separate positive and negative examples. So typically, decision trees are nonlinear classifiers. We have already seen an example of nonlinear classifiers built from scratch, right? Not based upon linear models, right? So neural networks will be viewed another example, right? We built a nonlinear classifier from scratch. Right? So here we're going to talk about four things. First, we're going to give some kind of formal definition of neural networks. What is neural networks? Right? Namely, what is hypothesis space? Right? So you see that the definition of neural networks is mainly up to its structure. It's essentially represents type of models have some kind of hierarchical structure. Then next we'll talk about how do we make prediction with neural network. Given a neural network model, given a new input, how do you make prediction? We call it forward pass. And then the main focus of this about neural network is to conduct training. You see that although we can just apply the stochastic gradient descent framework we have discussed previously for the training of neural networks, the major bottleneck is how to compute the gradient of the loss. Right? Because modern neural networks are usually quite large, right? It's not. It's very common to see like tens of thousands of parameters or even millions of parameters, right? So if you just want to compute the gradient naively, it'll be extremely expensive, right? How do we highly efficiently compute the gradient? This method is called backpropagation. Maybe you have heard that before, but we're gonna dive into the details of backpropagation, and you will be asked to implement the backpropagation algorithm by yourself. And finally, we'll talk about in practice, when you apply neural networks, what things do you need to be concerned? Okay? How do you choose the architectures? How do you choose the parameters? And also, you see that neural networks are a type of very, very expressive hypothesis space. That means it is they are always prone to overfitting, right? So the application of neural networks is to fight with overfitting. So you need to be careful to choose the architecture of neural networks and the training procedure, like early stopping, those kind of stuff. Okay. Any questions so far? Everyone's comfortable, right? Okay. So how do we start with neural So let us start with the linear threshold units. So we have shown this figure before. We said that, okay, the linear classifier, right? The linear classifier actually can be visualized as this figure, right? So suppose we got 4 features. So that means the vector x here contains 4 features, x1, x2, x3, and x4, right? So we can represent this prediction procedure in the follows. So first, for each input features, we have 1 node associated, but now here we didn't draw it explicitly. And then we also draw an additional constant feature 1. Okay? This is just to account for the bias. Okay? And then all those features, as well as this constant feature 1, are fed into a intermediate node, right? So which are drawn here, right? So connecting each feature, each input feature, and this intermediate node is an edge, and there is a weight on this edge. Okay? So basically x1 connecting to this intermediate node, and the associated weight on the edge connecting these 2 nodes is denoted by W1. Right? And similarly, on the edge connecting x2 and this node, we have weight W2 and W3, W4. And on the edge connecting the constant feature 1 and intermediate node, we have bias parameter B. So then we can define a rule to aggregate the information of those input features to the intermediate node. How can we do that? We just amplify each input feature by the weight associated on the edge connecting to the intermediate node. So that means, okay, when we send x1 to this node, we just multiply x1 with W1, right? And similarly, we send x2 to this node, we just multiply x2 with W2. We send x3, we multiply x3, W3. We send x4, we multiply x4 with W4. And finally, we multiply this constant feature 1 with bias parameter B. And then we just add up all the incoming messages, right? We get the result or the output of this node. So this gives us the prediction score here, right? W1, x1 plus W2, x2 plus W3, x3 plus W4, x4 plus 1 times B, which is W transpose X plus B, right? So actually, the computation of the value on this intermediate node gives us the prediction score, right? This is just definition. Okay? I just define a figure expressing how we compute those things. Okay. And then next, we're gonna feed the output of this node to the next node. Okay. And how do we get the output of next node? We apply a threshold function, which is sine function. Right? So we can see that the output of this second node will be the classification result, right? Because this intermediate results, the output of this intermediate node is the prediction score here, right? And then you feed this value to a next node here, which we apply the thresholding function to get output. That means this output is the sine of the prediction score, which is our classification result. Does it make sense? It's just a definition. Like it's just a graphical representation of this computation procedure, right? So you can see that we can use such a graph unit to represent, okay, first some linear combination of the input features with some bias parameter B, right? And then apply some thresholding function sine, right? So this is a general graphical representation for linear classifiers, and the training refers to estimating all the weights attached on those edges, which are W1 to W4 and bias parameter B, right? So we got different algorithms to estimate those parameters like perceptron, SVM, and other principles. Right? So now, this single we can view it as kind of like a basic unit. Right? It can be used to represent a linear classifier. Right? So if you want to construct a more expressive model, right, a more complex model, right, a natural idea would be, why not we use those graph unit as some kind of basic building block. We just combine different building blocks to make our model more and more expressive. Okay. That's how we construct a neural network. So basically, if we can view the input features here, x1, x2, x3, x4, as the output of other linear threshold units, so that we can connect different linear threshold units, right? And intuitively, by stacking those neural networks and connecting them, right, we might be able to largely improve the expressivity of our model. Right? So let's see how we do that, right? So in the standard linear threshold units, right, we assume that those input features x1, x2, x3, x4 are just from data, right? Are collected from data. They're data. So now we want to improve the model complexity. How can we do that, right? We want to use other linear threshold units to construct the input for this linear threshold units. So suppose our x1, x2, x3, x4 are still the data. Right? Now, we're going to first construct a linear threshold units, right, to generate one output. Right? So we use this output as the first input feature for the second linear threshold unit. Okay? And of course, we have to assign the weights on this linear threshold units, which generate input features for this guy, right? And then we construct another linear threshold units, right? And make another transformation of x1, x2, x3, x4, and 1 to get an output. We use this output as the second input feature of the linear threshold unit here. Right? And of course, the weights on the edges, right, for this second linear threshold unit are different from the weights on the linear threshold units used to generate the first input feature, right? They just we just employ another set of weights and bias parameters. And similarly, we can introduce a third linear threshold units and fourth linear threshold units, which transform the original input features the third time and fourth time to get the third input feature and fourth input feature for this final linear threshold units, right? And though we can then we can see that, okay, all those input features, right, here, are no longer the original inputs, right? They're new inputs or new input features generated from a set of linear threshold units applying on the data x1 to x4, right? Does it make sense? Right? So this is a natural way to combine those building blocks and to get more complex model. So now I want to ask, if you will this model as a whole, right? If will this model, the output here as a function of the original input features x1 to x4, will that model still be a linear model? Why? Yes, exactly, right? So you can see that by plugging into some thresholding function, thresholding function is a nonlinear function. Don't get confused, right? It's a step function, right? It's a nonlinear function. So after this nonlinear transformation, the whole model becomes nonlinear. Right? So you can see that it's pretty simple. It's like you're building Legos, right? You have some basic units. You just put them together and connect them together. You can build up whatever complex structure you want. Right? That's how in general neural networks are designed. So, but here, let us just look at this simple construction, right? So we call this guy, this whole model, as a two-layer neural network. Right? So first, the original data x1 to x4, also 1, is called the input layer. And the actual layer are the second one and third one. Right? So second layer is called the hidden layer. And third layer is called output layer. The output layer means that, okay, what is the actual output or prediction made by this neural network? Right? Sometimes people also call, okay, the output of the hidden layer as some kind of representation of the inputs. Why is representation of inputs? Because you can view the output of each thresholding node, right? It is kind of like transformation of the original data features, right? Or data input. So you can view like, okay, after some kind of nonlinear transformation, I got a set of new representation of the original data. Right? That's why people also call the outputs in hidden layers as the representation of the inputs. So it might be inconvenient to explicit draw two nodes, right? We first do a weighted summation of the incoming features, and then do some thresholding function over the summation, right? So in practice, to be convenient, we just merge these two nodes together. That is, if we compute the merged node's output, we first do the weighted summation of the input and then do some thresholding function, right? So this merged node is called a neuron. So when people talk about the neuron, it just means, okay, the neuron will collect the input features, maybe from data, maybe from output of other neurons, do a weighted summation and do a nonlinear function. Here is the thresholding. Right? Later we'll talk about other more commonly used nonlinear functions. People call it activation function. So now, if we count how many neurons do we have in this neural network, we actually have 5, right? This guy, this guy, this guy, this guy, and this guy. And we can follow this procedure, right? Right now, we construct a 2-layer neural network, right? But if we want to model the input of the hidden layer as the output of another linear threshold units, then we can construct an additional layer, right? So we can view like X1, now it's not X1, is output of linear threshold unit, which transform X1 to X4 again, right? We can do that again, so that we can make a 3-layer network, we can make 4-layer network, we can make 5-layer network. We are actually can construct as many layers as we want. Right? So any question regarding the construction of neural network? I believe it's quite intuitive, right? Okay, so now let's try to formalize this, right? How can we give a more formal definition of neural networks? Right? So, in general, we can view neural networks as a type of robust approach for approximating real valued, discrete valued, or vector valued functions. Okay, so that means your output, your final output, I mean, the neuron at the rightmost, right, which give you the final prediction, can give you a real output value, or can be a discrete value output, or can be a vector. And neural networks are among the most effective general purpose supervised learning algorithm currently known. Okay? And neural networks are particularly used for when you have like complex and hard to interpret data, such as real world sensor data, such as images, such as voices. Okay? So actually, those are the places where neural networks perform the best. And the training of neural networks, the key technique in the training of neural networks is called backpropagation, right? It has shown successful in many practical problems. So right now it's kind of like standard technique for neural network training. But how neural networks are invented? Actually, artificial neural networks were inspired by the biological neurons. Right? So in our nerve system, right, neurons are just the kind of core or basic components of the brain of the nerve system. So usually a neuron consists of a dendrite, right, that collect the information from other neurons, right, here, right, and also an axon that generate outgoing spikes. It's like edge, right? You're trying to send a message to other neurons, right? But don't get confused. There's only very rough analogy between biological neurons and artificial neural networks. Right? So modern artificial neurons are just inspired by biological neurons, but there are many fundamental differences. Right? Some serious biological neural experts won't admit artificial neural networks as a valid neural networks. So you can see that there's just a bit of like a similarity between that. Okay, you can see, okay, dendrites are those neurons and axons are the edges of neurons. But except that, there's nothing similar between the two types of system. Right? And more rigorously speaking, we should view neural networks or artificial neural networks as a type of functional approximators. I just construct functional approximators as a recursive or series of linear transformation and nonlinear thresholding or other activation functions. So artificial neurons or neural networks are functions that very loosely mimic a biological neuron. And in artificial neural networks, right, a neuron accepts a collection of inputs. Those collection of inputs made from data, right, maybe from data or come from the output of other neurons. We usually denote this collection of inputs by a vector x, okay? And then it generates an output by applying two steps. The first step, we do some dot product between the weights w and the input vector x, then add a bias parameter b. Right? So this is very similar to linear models, right? We do some linear combination of input features plus b, like bias parameter. Then we apply a transformation, and in most cases, this transformation is nonlinear, over the result of step one. And we call this transformation as an activation. So basically, the output of this neuron can be written as activation over this W transpose X plus B. So going back to our linear threshold units, right? So we know that the first step is computed here, right? It's a dot product between the weight vector and input vector plus B. Okay? And then the thresholding function takes the role of the nonlinear transformation, right? So the thresholding is actually the activation. Okay? Any questions so far? Everyone's comfortable? Okay. So someone asked, why should we use thresholding, right? Can we use other activations? The answer is, of course. Right? Actually, thresholding is not very commonly used in practice. Here are a set of more commonly used activation functions. So the first one is called linear unit. Linear unit basically doesn't do any actual activation function. It gave the z and then the output z. So basically, it doesn't do any transformation, right? And the thresholding is thresholding, okay. And then here are the three common used ones. Okay. Sigmoid. So your input is z, then the output is the sigmoid function of z. So the benefit of sigmoid unit is that, okay, no matter what kind of skew of z is, the output of the sigmoid is always between 0 and 1. So you can imagine that there are a bunch of like signal, right? And through this sigmoid unit, and it can squeeze the signal in the range between 0 and 1. And another common used, recently proposed activation function is called rectified linear unit. It's just max function, a max function between 0 and z. That means it truncates the negative part of z. This is also very, very popular. A third common used one is called tanh. Okay. So tanh function, basically, you squeeze the input signal z into the range between -1 and 1. And in addition to this, there are many other activation functions like sinusoid, sine, Gaussian polynomial, and so on. So basically, you can define your own activation function as well. Right? You can throw whatever activation function you believe is reasonable. And then the neural networks can be viewed as a whole model, right? As a holistic model, can be viewed as a function that converts the inputs to the outputs. This conversion procedure is defined by a directed acyclic graph. So basically, each neuron is one node in this directed acyclic graph. Right? And those neurons or nodes are organized as layers, and edges connecting different neurons or nodes, right, are associated with weights, and the parameters are those weights. So here I want to give an example, right? So from bottom to up, right? So this is the input layer where each node is an input feature, right? And this is a hidden layer, and this output layer, right? So you can see that we call each node in this graph as a neuron. Right? And the computation of each neuron, except the input neuron just come from data, right? Just input features. Except that, right, all the other neurons, the computation follows the rule we just mentioned. We first do a linear combination of the input features, right? With the summation W transpose X, right? And then plus a bias parameter B, then apply some nonlinear activation function to get the value of this neuron. And then we send these neurons to the next neuron in the next layer, right? Until we get all the results at output layer. But the whole structure of this network is directed acyclic, right? Because there's no cycles here. Right? You just compute. That's some kind of hyperparameter. You need to decide according to your application. Right? There's no answer on that. Other question? But basically, we can see that this network has a very clear structure, right? Layer, and one layer, the bottom layer, which is usually referred to as an input layer, feed their output to the second layer, and second layer collect the results and compute the results, right? Following the rules, right? And then feed their output to the next layer. We do this again and again until we generate the output layer's results. Yeah, we're increasing complexity. Yeah, that's something we're going to talk about next. But you already right now we're talking about the definition of the neural network, right? So in principle, you can make as many layers as you want if you believe this is necessary. Like in some like in image, a computer vision domain, some like very successful neural networks can contain like 250 layers, right? And of course, there will be some issue in the training, right? So people propose some other architectures to relieve that problem, like ResNet, right? But those layers can be very can be many, and 250 layers will contain like millions of parameters. Okay, so to define a neural network, right, we need to specify the following. So first, we need to specify the structure of the graph. That means you need to determine how many layers do you have, and what is the width of the layer, right? How many neurons do we need to specify for each layer? So it's totally up to you. There's no you have a maximum flexibility to design your network, and of course, those structure design is often dependent on the application. Right? It's not hard to, it's not easy to find the best structure on that. Right? And they also need to determine the activation function on each neuron. Right? You want to use sine function, you want to use tanh, you want to use rectify linear. Right? It's up to you. Right? So usually people will choose the same activation function for every neuron, but in principle, you can vary the activation functions for different neurons. It's totally up to you. Right? So once you specify the structure of the network and also the type of activation function, we call, okay, you have specified the architecture of the network. And this architecture typically is predefined. Then the parameters of the neural network are all on the weights on the edges. So you can imagine on each edge, which connecting two neurons, right, there is one weight, right? And you need to use some data-driven approach to estimate appropriate values of those edge weights. And once you have identified those edge weights, you actually have identified the neural network parameters. Now, then you can combine your values of those weights and your architecture of the network to make prediction. again, you have to choose by yourself. We just random draw 3 neurons here, but in practice, you might choose to use 100 neurons or 200 neurons. Yeah. No, like, okay, this one is fixed, right? Because it is determined by your data, right? But the width of the hidden layer, you can vary flexibly, right? This one could be 100, this one could be 200, right? Could be 3, could be 30, whatever. It doesn't matter. Right? And you need to decide how many neurons you want in your second layer. Other question? Okay. So here's a brief history of neural networks, right? You can see that the invention of neural networks can be traced back as early as to 1940s, right? And those are about linear classifiers, right? In 50s of the last century, Rosenblatt proposed the perceptron algorithm for single threshold union, which is essentially for linear classifier, right? And then in 1980s, then people develop other neural networks like feed-forward and also convolution neural networks. This incurred a first boom of the neural networks, right? And then until 2003 to today, with the more and more powerful computational resources, the more and more data, people find that find the advantage of neural networks because the training becomes a lot more easier, especially with like computational libraries like PyTorch, TensorFlow, JAX, all kinds of stuff, right? You actually really don't need to manually compute the gradient and perform those stochastic descent, right? So, and also you have clusters, you have GPUs, all kinds of stuff. All those enable neural network to handle a lot more data than before. Then people find out the power of neural networks. So next, we're going to talk about what's the expressivity of neural networks. So we will like as one type of model. Of course, neural networks have their own hypothesis space. Right? So we would like to know, okay, what kind of functions do neural networks represent? Right? We know that a single threshold unit or single neuron, right, which is linear classifier, only represent linear classifier. Sorry. Given these two set of examples, positive and negative, it can only draw a line or a hyperplane to separate them out. Right? That's the set of functions a single neuron with thresholding activation can do. Right? However, if we stack those thresholding units into 2 layers, then it can represent arbitrary convex polygons. You can see that it's typical from the clustering boundary, right? It's a typical nonlinear classifier, right? You just add one more layer. Right? What if we add another layer, like 3 layers with thresholding activations functions, right? So it can represent an arbitrary union of convex polygons. Right? So you can see that we add one more layer, it becomes even more expressive. In general, we can view neural networks as the so-called universal function approximators. There's some theory, a very famous theory, published in last century. Right? So in that theory, we claim that any continuous function can be approximated to arbitrary accuracy using a neural network with only one hidden layer with just the sigmoid units. So basically, you don't need to like use many layers, just one hidden layer, and just use the sigmoid activation function. As long as the width of the layer is enough large, it can approximate any continuous function at arbitrary accuracy. It's very powerful. Right? And later people find that, okay, you even do not need to restrict your activation function to be sigmoid. You can use tanh, you can use others, right? So approximation error is insensitive to the choice of the activation functions. And here, give an example, like two-layer threshold networks can express any Bloom functions. So remember, decision trees can do this as well, right? We'll talk about that, right? If we have a decision tree, we can use that to represent any Bloom function, right? And here we have another conclusion, like if you have like two-layer threshold networks, these networks can also express any Bloom function. So here's the visit dimension of the threshold network with edge E. So this dimension is proportional to the size, the number of edges times the logarithm number of edges. So you can see that the more neurons you have, the more edges you have, the larger the visit dimension, right? That means the more expressive, the more complex your model have, right? And if you use sigmoid activation instead, then the visit dimension doesn't have some analytical expression, but we have some upper bound and the lower bound. So it's upper bounded by the number of the square of the number of the neurons times the square of the number of edges, as lower bounded by the square of the number of edges. So again, those reflect that the larger the size of your neural network, the more expressive the network it is. Right? Any questions so far? Everyone is comfortable, right? Okay, so I'll leave an exercise for you. Right? If we choose our activation function as identity mapping, that means I don't do actual nonlinear transformation. Like my input is Z and the output Z. Then no matter how many layers do we have, the expressivity of neural networks is the same as a linear classifier. Yeah, I'll leave it as an exercise for you. Okay. So now we finished the definition of the neural network. Next, we're going to talk about how to make prediction. So far, we talk about how do we construct neural network, right? There's as long as we define a cyclic graph, like organize the neurons layer by layer, right? And we have some computational rule to compute the value of each neuron, right? Weighted summation plus B, right, of the incoming features, and then perform some nonlinear activation function, right? And then we'll talk about expressivity, right? Next, like given a particular neural network, right, and given some input data, right? How do we calculate the prediction? Of course, this is a basic requirement if we want to apply our neural network for prediction tasks. Right? So let us consider an example network. So this is just a two-layer neural network. And for convenience, we're going to introduce the several naming conventions. So we represent the neurons in the input layer by X, and the neurons in the hidden layer by Z, and neurons in the output layer by Y. And those shaded neurons or nodes are just constant feature 1, right, to account for the bias parameter. And also, we consider the sigmoid activation function. And then in the output layer, we use the linear activation function. In other words, in the output layer, we do not actually perform any nonlinear transformation. So basically, we'll compute y. They'll just do a weighted summation of z0, z1, z2. This is just the tradition of the neural networks. In the neural network community, to compute the output in the output layer, we don't do any nonlinear activation function. But that does not mean you cannot do that. You can do that. But here we just follow the tradition. And only perform nonlinear activation function on the hidden layers. And then how do we index the edge weights? Right? So we're gonna introduce a little bit naming convention, right? So the superscript indicate the target layer. Okay. And in the subscript, we have two indices. Okay. The from index, simply meaning that the index of node coming from, right? And then the to index indicates the node of the edge pointing to. Right? So if we take a look at this particular edge weight, right, W, right? So the subscript indicates the target layer, which is output layer, right? So we use O as the subscript, right? So in the here, right, the from node or starting node are coming from Z0. So the from index is 0. And this edge points to the first output neuron in the output layer, so which we index 1. So the to index is 1, right? So the subscript is 0, 1, right? And superscript is 0, is O, right? And similarly, if we take a look at here, right? This neuron, right? So we know the target layer is a hidden layer, so the superscript is H, right? And this edge connects from X0 to Z1. So in the subscript, it is 0 and 1. Right? From index 0 and target index or to index is 1. Does it make sense? Okay. So now with those notations in our mind, right, we can talk about how to predict with the neural network, the so-called forward pass procedure. Right? So given the input X, right, X consists of X1, X2, and X0 here is constant 1, as we just mentioned. Right? What we need to do is that from the input layer, that is bottom, to compute each neuron in the next layer, one by one, until we compute the output neuron in the output layer. So given X0, X1, X2 here, right, we know that they are from data, right? The first neuron we're going to compute in the hidden layer is Z1, right? Remember, Z0 is 1, right? It's constant 1, right? So how do we compute Z1? Following the definition, right? We're going to first do the weighted summation of the incoming features, which are X0, X1, and X2, right? Which are W0, 1, H, which is the edge weight connecting X0 and Z1, right? Remember, X0 is essentially a bus parameter, which is bus feature 1, right? So this is essentially W0, 1, H times 1, right? And plus this edge weight times X1, this edge weight is denoted by WH11, right? Connecting X1 to Z1. So the subscript is 1, 1. Right? Target layer is H, right? Times X1. And this input feature X2 times the edge weight connecting X2 to Z1, right? Edge weight connecting X2 to Z1 is denoted by W21H. Okay? And then once you got this weighted summation of the incoming features, and then you apply the nonlinear activation function, right? Here is the same old function. You got the value of the neuron Z1. Does it make sense? Let's just apply the rule, right? And then similarly, you can compute Z2, right? Again, do a weighted summation of the incoming features, Of course, the weights on the edges connecting from those incoming neurons to Z2 are different, right? But you follow the same rule to compute Z2, right? Once you get this linear combination, you apply the nonlinear activation function sigmoid over the linear combination, right? You get Z2, right? And then you got the values for Z1 and Z2. Oh, Z0 is constant feature 1, right? So now you have the values of all the neurons in the hidden layer ready. Then we're going to use those neurons to compute the neurons in the output layer. There's only one neuron in the output layer, which is Y, and the computation is the same, except that, remember, we just discussed, right? So in the output neuron, we don't apply any nonlinear activation function. We just do a linear combination, which is W010 times Z0, which is 1, right? W110 Z1 times X1 times Z1 here, and the W210 times X2 here. You just add them together, you get your output neuron, which is your final prediction. Any questions so far? It's straightforward, right? Okay. Yeah, that's a forward pass. Of course, if you have multiple layers, right, multiple hidden layers, not only one hidden layer, you got a second hidden layer, of course, and then you need to use Z0, Z1, Z2 to compute every neuron in the next layer. And then once you got the neuron values for next layer, use them to compute the neurons in the next layer until you reach the output layer. Okay. Then we start to talk about the training procedure. Of the neural networks. Right? So as we just mentioned, right, the training of the neural networks relies on so-called backpropagation technique. But before that, we need to discuss about the general setting, general training setting for neural networks. Right? It's very similar to the training setting of other models. Suppose we're given the design of neural network. That means we have specified the network architecture. Right? We have designed the layout of the neurons. How do they connect to each other, and what's the definition of the activation function, right? And also we have collected a data set of label examples, right? Basically, you can view as pairs of the input features and the label, right? So x1, y1, x2, y2, in general, xi, yi. And the goal of the training is to learn the weights or the edge weights of the neural networks according to the data set S. Right? And here, if we will the final output of neural network, right, the output neuron, its value used as our prediction, right? If we view the output of neural network as a function, right, it is not only a function of the input x, but also a function of the edge weights W, right? If you consider computation of the neural network, consider forward pass, right? So your input feature X will first conduct a weighted summation, right? And then feed to the next layer. And when you compute, we will finish computation of neurons in the next layer. Then you do a weighted summation of the next layer to compute the neuron in the next layer, right? So all those computation will involve those edge weights. So basically, and eventually, the output of neural network is not only up to the input X, right, in the bottom layer, but also all the edge weights, because all the edge weights are involved in the computation of the output. So in other words, we can view your final prediction y as a function not only of the input feature vector x, but also the neural network parameter w. This is a very important insight. But this function is quite complicated. And then, based on this observation, we can construct some kind of training loss on data, right? And then we minimize the training loss with respect to the model parameters W here, namely the neural network weights, right? And then we conduct our learning. Right? So use the loss minimization framework as we use for perception, as we use for SVM, right? So we have a classifier neural network that is completely defined by its weights. Okay? So we can construct a loss function over the training data, meaning that for every training example I, we can use our neural network given the input training input xi to make prediction, right? Then we can evaluate the loss in predicting the ground truth label yi, right? And then we just sum over the loss on all the training examples, we get our loss function on the data. And perhaps we can add a regularizer to penalize W, right? Like, for example, I can, similar to SVM, I can add a norm of the weight vector, norm of the weights. But anyway, we can construct a loss function of the neural network on a set of trained data. Then the learning amounts to minimizing this loss function with respect to the neural network weights. Does this framework make sense? Any question? Hey, this is very similar to what we have done previously, right? Except that, okay, we just change the prediction from a linear classifier to a neural network, right? And so far, we have used this strategy to work for learning of support vector machines, perception, least mean square regression, and for each model, the loss corresponds to a different function, right? For example, in SVM, the loss is not square loss, it's a hinge loss, right? So although all those are linear models, right, we can apply the same idea for the nonlinear models, namely neural networks. Any questions so far? Or talk about the general training framework. Okay. So now, let us back to the concrete example, right? This is our running example, right? This is a two-layer neural network. And we, for any input x1, x2, right? Through this forward pass procedure, we can compute the prediction, right? So you can see that the prediction or the output y is determined not only by the x1, x2, but also on all the edge weights. Right? And for a particular input x1, x2, right? Suppose the true label for this example is y star, right? And then how do we define a loss based on our prediction y? Any thought? Let us assume it's a regression test. So y is continuous. Yeah, exactly, right? So like what we have done for least mean square, right? We want to compute loss, we just measure the difference between your prediction and the ground truth. Okay? And for convenience, we just take square of that and put a half as a constant in front of that. And of course, you can define other laws, right? You can use absolute value, or you can take cubic if it doesn't sound that crazy, right? But for convenience and practice, we usually use this square laws again. And then the y itself is a function of not only the input x, but also all the weight parameters, right? So that means we can calculate loss, the square loss over all the training examples, and then we have a loss function, and then we just minimize the loss function. And then how do we minimize the loss function? Right? In other words, how do we solve the optimization problem? What kind of framework can we use? Gradient descent, right? But as we discussed, right, neural network, in most cases, are applied to a very large data set. Right? You might have millions or even billions of training examples. Right? Using exact gradient descent will be very, very inefficient. So here we're going to choose the stochastic gradient descent framework. Right? And the framework is the same as we used before. Right? So this is our loss function for the whole training set. Right? And then we're going to initialize the neural network parameters, right, randomly. Then we go through big T epochs. Right? Each epoch meaning that you're going to go through the whole data set once, right? Inside each epoch, we first randomly shuffle the training set. Then we go through every training example one by one. Right? Then we treat this example as the entire data set. Then we compute the gradient of the loss on this particular example. Right? Then we update the neural network parameters according to this gradient. Right? This gradient is also called stochastic gradient. Right? Of course, we need to consider the step size gamma t, right, or learning rate gamma t, as we mentioned before, to ensure the convergence of your stochastic gradient descent. You have to schedule a gamma t to satisfy several conditions, right? The summation of gamma t must diverge, and the summation of their squares must be bounded, right? So as long as you have a smart schedule of a gamma t's, then applying this stochastic gradient descent procedure will guarantee you to converge to some local minimum. Right? But here we want to emphasize that, I mean, although this procedure looks exactly the same as we use for SVM, as we use for least mean square, right? One different point is that the objective function here, namely the loss function here, is non-convex. Remember, in the least mean square problem or in SVM, we're always using convex objective function, right? So that means no matter how you initialize your parameters, at the convergence, they converge to the same global minimum. But neural network is different, because the neural network mapping here, right, given some input xi, given the model parameters, you make a prediction. This is done through a series of linear transformation, nonlinear activation, linear transformation, nonlinear activation function, right? So this function essentially is overall is very, very complicated and usually non-convex. That means it might converge to different local minimum. Right? If we can write down the loss landscape or landscape of this objective function, it might be look like this. Right? It's very complicated. So that means where it eventually converges to is sensitive to the choice of initialization. Okay? If you initialize the parameters here, then you might converge here, right? If you initialize your parameters here, you converge here. Okay? So that means the initialization of the neural networks really matters. Right? So in practice, you will see people have fun many different types of initializations, and some initializations are named after their name. Like some Chinese people invented a very popular initialization. His family name is He. So you see that in PyTorch library, there is a so-called initialization methods called He initialization. That's very interesting. So basically in your practice, you need to choose several popular initializations and test which one give you better performance. My next question is, have we solved everything? Right. Which step is still missing? Yeah, exactly right. Actually, I haven't touched the core step, right? Given a randomly sampled training example, right? How do we compute the gradient of this loss, right? Actually, this is the critical step. Right? Only when you are able to efficiently compute this gradient, you can drive your stochastic gradient descent procedure, right? Let us first consider the type of activation function, right? If your activation function is continuous, meaning like tanh or sigmoid, they are continuous, and also this linear combination of those are continuous, so then the whole neural network will be a continuous function, it's differentiable, then we can find the gradient in principle, right? But if your activation function is discrete, like ReLU function or rectified linear function is a max function, right? It is not continuous, or sine function is not continuous, right? It's not differentiable. How can we do that? We can use a stochastic subgradient, right? But the problem is in the size of neural network. If the neural network is too deep, right? For example, you contain like 200 layers, right? And then you can imagine this neural network mapping, neural network function is highly complicated, right? And how do we compute the gradient of the loss with respect to every parameter? Right? Of course, you can compute them one by one, right? But you can imagine, suppose you have 1 million parameters. Right? For one function, you need to compute the gradient, the partial derivative over 1 million element, right? Even for one example. Right? This is by no means efficient at all, right? Even for stochastic gradient descent, right? We talk about, okay, every time at least you sample one example, right? You use that to construct a loss function, you compute that loss function with respect to every neural network parameter. However, your neural network contains 1 million parameters. I mean, you have to go over 1 million elements and to calculate the partial derivatives. That is really, really expensive. Then the question is, how do we efficiently finish computation, right? Without computing each partial derivative from scratch. So this efficient algorithm is called back propagation. So before we dive into the back propagation's detail, right? We just check where we are, right? Just a step back and look at where we are before we start, right? First, if we can, the whole setting is as follows, right? If we have a neural network, like we have a specified structure, we have specified activation and weights, then we can make prediction for input following the forward pass, right? And then if we have a true label of that input, then we can define a loss function for that example by just measuring the difference between your prediction and the ground truth, right? And now we have a loss function over the training data, right? Then if we can take the derivative of the loss with respect to each of the weights then we can get the gradient, right? Then we can apply the gradient descent over stochastic gradient descent over the neural network training, right? So any questions so far about overall setting? Okay, everyone is ready? Okay, let's stop here today. Yeah. And next week, we're going to talk about the details about backpropagation. You see that backpropagation essentially is a smart leverage of the chain rule, which we have learned from our calculus 1.